A few years ago, Tesla didn't just improve electric cars, they rewrote the rulebook. It wasn't about flashy design or futuristic styling. It was something far more important, the battery. Tesla introduced the structural battery pack, a breakthrough where the battery itself became part of the car's frame. This single move made EVs lighter, stronger, and more efficient. And as expected, the rest of the industry quickly tried to catch up. But now, a US-based company called 24M Technologies says they've gone even further. They claim their new battery design could power an electric car for 1,000 miles or 1,600 kilometers on a single charge. Yes, 1,000 miles. So how is that even possible? And could it actually work in the real world? Let's break it down. The idea of a structural battery pack wasn't just an upgrade, it was a turning point. Before Tesla introduced it, EV batteries were built the old-fashioned way. Thousands of tiny cells stored in modules, then placed inside large battery packs full of heavy casing and support materials. Most of that structure added weight, not energy. Tesla flipped that idea on its head by making the battery part of the car's structure. Instead of sitting inside the frame, the battery became part of the frame. This meant fewer materials, a stronger body, and way more room for energy cells. The result? More range and better efficiency without increasing size. Naturally, other automakers rushed to follow. Chinese giants like BYD, KTL, and NIO came out swinging with their own cell-to-pack or cell-to-body designs. They created all kinds of flashy names, CTB, CTP, and more. But the concept remained the same. Remove unnecessary parts, and use space more efficiently. This approach made EVs lighter, cheaper, and easier to build. But it wasn't flawless. Even with these new designs, a surprising amount of space inside battery packs was still taken up by parts that didn't store any energy. And that's the exact problem 24M Technologies wanted to solve. Here's the hidden truth behind modern EV batteries. Even with structural packs, there's a huge amount of inefficiency. Inside each battery pack are hundreds or even thousands of individual cells. Every one of those cells has its own metal or plastic casing to keep it safe. These casings are essential for preventing short circuits and managing heat, but they store zero energy. According to 24M Technologies, only 30% to 60% of a traditional battery pack is actually storing energy. The rest? Wasted space structural material, safety layers, and packaging that does nothing to power the car. This means there's a lot of potential energy left unused. Even though engineers have made great progress in improving energy density and charging speed, the overall design has stayed the same for years. To truly leap forward, something more radical was needed. A complete redesign of how a battery pack is built from the ground up. That's where 24M comes in. Instead of thinking about batteries as lots of small cylinders or pouches inside a box, they've designed something entirely new. Their idea removes the cell casings altogether and integrates the energy storing parts directly into the battery pack itself. 24M's Electrode-to-Pack revolution. 24M Technologies, based in Massachusetts, has developed a concept they call Electrode-to-Pack or ETOP. It's a fresh way of thinking about energy storage. In simple terms, ETOP removes the middle layers, no separate battery cells, no modules, no heavy casing. Instead, it takes the core components that actually store energy, the anode and cathode, and builds them straight into the pack structure. The electrodes are sealed and arranged directly within the battery housing, becoming part of the system itself. This means there are no wasted materials like metal shells or plastic containers. Every bit of space can be filled with energy-storing materials. According to 24M, this design could make up to 80% of the pack's volume active, compared to only 30–60% in current batteries. That's a massive jump in efficiency. The result? Potentially double the energy density. That's why 24M believes a 100-mile range is possible using this approach. It's not about new chemistry like solid-state or sodium batteries. It's about smarter design. The simplicity of ETOP also promises lower production costs, fewer materials, and easier scaling once factories are built for it. On paper, it sounds like the next big leap after Tesla's structural battery. Why this matters for America? 24M's idea isn't just about longer range. It's about competition. The company has stated that the US must innovate faster to keep up with Chinese battery giants like KTL and BYD. These companies already dominate global battery supply, offering cheaper, high-performance lithium iron phosphate, LFP, and sodium-ion batteries. As exciting as it sounds, 24M's concept isn't ready for mass production yet. One of the biggest hurdles is manufacturing scale. Right now, the global supply chain for batteries is built around familiar designs: cylindrical, prismatic, or pouch cells. Entire factories, supply chains, and quality control systems depend on these shapes and processes. Switching to an electrode-to-pack method would mean redesigning everything from production lines to safety testing. That could cost billions of dollars. Manufacturers would need strong proof that this new system is worth the investment. Another major concern is repair and maintenance. Traditional battery packs can isolate damaged cells without affecting the whole system. If one cell fails, technicians can replace that module. But in 24M's fully integrated design, there are no separate cells or modules. So, what happens if part of the pack fails? If one section malfunctions, could it take down the entire battery? Would mechanics need to replace the whole thing? That's unclear right now, and it's one of the most serious practical concerns for real-world use. Despite these challenges, the potential benefits, longer range, higher density, and lower costs, make this technology too promising to ignore. Could this actually work? When you first hear 100-mile range, it sounds unrealistic, but technically, it's possible. Remember, 24M isn't changing the chemistry, they're just using the space better. If they can fit twice as much active material in the same size pack, they can roughly double the range. The company claims this approach could work with existing lithium-ion materials, meaning automakers wouldn't need entirely new raw materials or supply chains. That's a huge advantage. Still, proving this in real cars will take time. Battery technology is one of the toughest fields to commercialize. Many companies have promising lab results but fail to scale. Mass production requires years of testings, safety, validation, and real-world trials. 24M has been developing advanced lithium-ion designs since 2010, and they're known for practical, step-by-step innovation. That gives their claims more credibility than startups promising magic solid-state solutions. If 24M can demonstrate consistent safety, efficiency, and recyclability, their electrode-to-pack batteries could completely redefine how EVs are built. It might not happen overnight, but this could be the next big step in the electric revolution, just as Tesla's structural battery once was. Conclusion: innovation in batteries has always driven progress in electric vehicles. Tesla's structural pack showed how integration could unlock more power and range. Now, 24M's electrode-to-pack design aims to push those limits even further, eliminating waste, reducing cost, and potentially giving EVs an incredible 100-mile range. But challenges remain. Scaling up production, ensuring safety, and building repairable systems are no small tasks. Still, even if the full 1,000 miles isn't achieved immediately, any improvement in energy density is a huge win for the industry. This new direction could reshape how electric cars and even aircraft are rebuilt in the future. If 24M's idea works at scale, it won't just extend range. It could redefine what's possible for sustainable transportation worldwide. The next evolution in battery design may have already begun quietly inside a Massachusetts lab.